In this problem, we have a car on a banked road that is turning. We want to determine what is the maximum speed with which the car can turn safely. And the coefficient of friction between the road and the tires of the car is given to be 0.8, and the radius of the curvature, or the turning radius, is 50 meters. Since it's turning, it's moving, it can be considered to be moving in a circular path, and so we are involved in solving a circular motion problem. The first thing to uh, understand is the direction of the centripetal acceleration in this case. As we know, the centripetal acceleration is always directed toward the center of the circle. So if you have a circle right here, then and the object is moving in that circle, at every point on the object will be pointing towards the center. The object acceleration will always be pointing towards the center of that turn. So where is the center of this curved surface of this banked road here? Well, if the acceleration was down along the plane, then to move in a car, that would mean that the center is below the surface of the road. That is unphysical, right? That cannot be the case, because when you turn on a banked road, you don't go underneath the road. Hence, it is only logical that the acceleration, or the center of the curvature, center of the turn, is on the surface of the road, on the horizontal or the surface of the road. So we say that the center is somewhere around here, and the turning radius is 50 meters. So the acceleration in this case would be pointing this way, okay, towards the center. Now, our next job would be a bit tricky, because we have never solved a problem so far that involved the acceleration to be um, to not be on the inclined plane. The acceleration is now completely horizontal, regardless of the presence of this incline. Okay. To solve this problem, to make our lives easier, what we do is we choose an axis. One of the axes points in the direction of the acceleration. So we choose this kind of axis, the usual plus x and plus y that we use for horizontal kinematics or dynamics problems. We will use here as well. Okay. Now, what is the next thing we do? Next thing, as always, since we're dealing with force, we draw the free body diagram. Let's go ahead and do that. So, what would the free body diagram of the car look like on this banked curve? We have done these sorts of problems before, but in this case, the problem would look a bit different, since the axis is not chosen along the inclined plane. As usual, we'll have the weight of the car pointing vertically downwards. Weight is mass times gravity. And we'll have a normal force that the road exerts on the tires of the car. And we would then have the acceleration. Remember, will be pointing in this direction, but in the free body diagram, it's not necessary to draw an acceleration, because free body diagram only has forces in it. However, I'm just mentioning it to remind ourselves that the acceleration is in this direction, and our choice of axis is also along the acceleration and perpendicular to the acceleration. Okay. Let's consider this problem without friction first. Okay, no friction, meaning mu can be neglected. The coefficient of friction can be neglected. Now, what is the next thing we do in these problems when forces are not aligned with our chosen coordinate axis? We break the forces down into its components. Let's go ahead and do that. Which of the forces here have components that are not along our x or y axis? It's the normal force right here, because it's perpendicular to the plane, while the axis is not along the plane, right? So we have to break n down into its components. If we do that, we'll have components that look like this. This would be the y component, or the vertical component, ny. This would be the x component, or the horizontal component, nx. Our next job would be to find what ny and nx is. And remember, we know that This is 30 degrees from the question right here. And so if this is 30 degrees, with geometry we can check that this is also 30 degrees. Okay, so we know the angle between the components and the resultant normal force. So we can draw a right angle triangle like always, where the components are ny and nx, forming a right angle, and then we have the resultant normal force forming the hypotenuse. Okay, now the normal force, then if this is 30 degrees, then we can check using trigonometry that nx, the x component, which is the opposite of this right angle triangle, opposite side of this right angle triangle, will come out to be the hypotenuse, or the magnitude n times sine of 30, the angle here, and ny is n cosine 30. Alright? Next job will be to write down Newton's second law in the x and y directions. In the x direction, what do we have? We will have summation of f in the x direction equals to m times a in the x direction, which leads to, what are the forces in the x direction? If we look at our free body diagram, we have nx and nothing else going in the x direction, right? Because our x direction is this way, horizontal. There is no other forces, so we write nx equal to the mass of the car, m times ax. What is the acceleration in the x direction? Remember, it is the centripetal acceleration. Let's keep it as mac. Alright? Now, let's call this equation 1. In the y direction, what do we have? In the y direction, summation of fy is equal to 0. Since there is no acceleration in the y direction, the car is not bobbling perpendicular or up and down the vertical. So the acceleration in the y direction is 0, which leads to, what are the forces in the y direction? We have ny and we have mg. Ny is in the positive y direction, while mg is in the negative y direction. So the summation becomes ny minus mg equal to 0, right? This leads to ny equal to mg. Now, what was ny? Ny was n cosine 30. So we can write for ny, in place of ny, we can write n cosine 30 equal to m times g. Okay. Now, what is our goal? Our goal is to find the speed, the maximum speed with which it can turn safely without falling over. Remember from our work in centripetal motion so far, is we know that the magnitude of the centripetal acceleration is given in terms of the speed and radius. So AC is equal to v squared over r. So we can solve equation 1 by replacing AC with v squared over r to give us v. But if we look at equation 1, we see that nx is also an unknown. Nx can be written in terms of n, the total magnitude of the normal force. However, we don't know what this n is. So we want to eliminate n from this equation, since our target is another unknown, which is inside AC, in other words, which is v. So we simplified this equation a bit more and solve for n. N becomes, if you divide both sides by cosine 30, n becomes mg over cosine 30. Now, wherever you see n in equation 1, plug this expression in, okay? And for AC, replace AC with v squared over r. So we have from 1, n sine 30, because nx is, remember, n sine 30, equal to mv squared over r. What is n? N is nothing but mg over cosine 30 times, this is sine 30 is as before, sine 30 equal to m v squared over r. Now since both terms have m in it, we can divide m's out, so the mass of the car is not relevant in the problem, and we know that r is 50 meters, therefore we can solve for v. We solve for v squared first, which gives us g sine 30, meaning what we are doing is we are just cross multiplying r to this side of the equation. So g sine 30 times r is 50 over cosine 30, right? This one right here. G is 9.8, and if you square root both sides, this 2 goes away, and you get the square root on this side, and this gives us the speed, the maximum speed with which the car can turn safely without tipping over when there is no friction. Comes out to be 16.9 meters per second. Okay. Now let's consider the problem with friction. Okay, without friction, well, it is not really realistic for cars to be able to turn safely on a bank curve, because friction actually helps us maintain balance. But regardless, this is a simplified scenario, so this is the safe speed for when there is no friction. What happens when there is friction? Well, there are two scenarios. First scenario is whenever there is friction, you have to to determine the direction of friction, you have to first remember that friction will always oppose any sliding motion. Okay, so if you were about to slide this way, slide up along the plane, then the friction would be down along the plane. If you were to slide down along the plane, then the friction would be up along the plane. Alright? Okay. But when when can we know that, how can we know that the car will be tipping one way or the other? Will it tip up along the curve or down along the curved surface? Well, uh, if it goes, if it is not, if it's moving at a safe speed, it is moving at a low speed, then the the car will they will follow the general inclination or general tendency of any mass to slide down. Okay, that means the friction would be acting up along the plane, meaning the friction will actually help it maintain balance. Okay, so therefore this is why it is safe to turn at a low speed. But if you were in the car driving and you are going too fast, what would happen is the car would be trying to tip over on this side. Alright, so the friction would be opposing that tipping over or sliding up along the plane by acting downwards. These unbalanced force can cause the car to flip over the curve. Okay, that is not something that we want. In this scenario, we assume that car is going very fast. Okay, so in that case, what would be our free body diagram? Let's see. We have the incline. The car is sitting on this incline. What are the forces on it? Well, the first force is the weight of the car, mg. Then, as usual, it will have a normal force exerted on it by the road, and then since it's going at a very high speed, the car would be trying to tip over on this side. Okay, So that there is no such thing called the tipping over force that you would draw on this free body diagram. There is no other forces apart from friction that will either uh, be successful in helping you maintain balance, or it will fail miserably and cause you to topple over and uh, could lead to some fatality. Okay, so it's a good practice to not be so faithful in friction and go at a slow speed. However, in this scenario, the car is going too fast, so the natural inclination of this car would be to tip over on that side, okay, up the plane. So friction, let's use a different color for friction. Uh, just, just being pedantic. Let's use this color. Friction would be down along the plane. Okay. Our axis is like before, the same that we had before. It is the usual plus x plus y, and the acceleration is in this horizontal direction along the x-axis. So our job would be to break the forces down which are not along the x or y axis. So what are those forces? N and F. So let's break N and F down. We have already done that for N in the previous part, which this would remain the same. Okay. So it would go up and to the left, N Y, N X, and we have already worked out what Nx and Ny has. What are the magnitudes of Nx and Ny? So our next job would be to find the components of friction, which is what we are going to do. Let's use a different color again. Alright, so how would the friction components look like? Well, this friction is down along the plane. So X component would be going to the right. This is Fx. And the Y component would be going down, right? Because it is actually acting downwards. So these are the friction components. And remember, we know this angle right here, 30. If this is 30, then this angle, subtended by Fx and F in purple, will also be 30. Okay. So let's draw the friction triangle more clearly. We have here Fx, the friction component in the x direction. We have here Fy, the friction component in the y direction, and we have the resultant or total friction, which is the hypotenuse of this triangle, and we know that there's a right angle between the components, and also we know that this is 30. If this is 30, then again we can use trigonometry. So opposite of 30 is Fy. Therefore, this means that to relate F to Fy, we would need sines, because opposite over hypotenuse. So what is, let's again change back to colors. So what actually is Fy? Fy is F times sine 30. What is Fx? Well, if this is sine, then Fx is just cosine. F times cosine of 30. Okay. Now we are ready to write down Newton's law in the x and y directions. Let's go ahead and do that. What do we have in the x direction? In the x direction, we have summation of Fx equal to m times a in the x direction. This leads to, what are the forces in the x direction? We have Fx in the x direction. We have Nx in the x direction. So now we have two forces in the x direction. Let's sum them up. And both are in the positive x direction. So we would have Nx, which is n sine 30. Let's just write that. And that is added to the x component of friction, which is just, we found, was F times cosine of 30. There are no other forces, so this is equal to the mass of the car times the acceleration, the x direction, which is just the centrifugal acceleration. Okay, let's call this equation 1. Now, what is Newton's second law in the y direction? As usual, there is no acceleration in the y direction because the car is not moving in the y direction. So we can just write the summation of Fy is equal to 0, right? What are the forces in the y direction? We have Ny, we have Fy, and we have Mg. Ny is directed upwards, so positive. Fy is directed downward, so it's negative. Mg is also directed downward, so that's also negative, right? So we end up with Ny, which is n cosine 30 plus, or actually this is not plus because both of the other forces are in the negative y direction, so actually minus Fy, which is f sine 30 minus Mg equal to 0. Let's call this equation 2, and let's move to a new page. So this is what we have. We have the two equations that we need. Now let's remind ourselves what are the definitions that we know about friction. We know that friction is defined as being equal to mu times n. Well, it is actually defined as a limit, but in this case we can consider the friction, the static friction, to be the maximum, since this car is at the point of tipping over. Okay, that is what we are considering to find the maximum speed. So F is mu times n, where mu is the coefficient of friction between the surface and the tires of the car, and n is the normal force. Okay. So similarly, we can define the components of friction. Fx is defined as mu times nx, the x component of the normal force, and Fy is equal to mu times ny, the normal y component of the normal force, right? So, but we have already written our equations in this format, hence we only need the total magnitude of friction. The total magnitude of friction is just mu times n. So equation 1 can be rewritten as n sine 30 plus f cosine 30. In place of f, write mu times n. Mu is just 0.8. Let's write 0.8 times n, and it was multiplied to cosine 30, so we keep that, and this is equal to MAC. Okay? Our goal now, let's first find the centrifugal acceleration, and then we have in equation 2, this is 1. Equation 2 will have n cosine 30 minus f sine 30. F is again 0.8 times n sine 30 equal to m times 0, actually, which so we can bring mg on that side of the equation. Let's write it as mg. Okay, so these are equations 1 and 2. Now our goal is to find this AC, and we see that both of these equations have two unknowns, n and AC. So like in the previous part, we want to eliminate one of the unknowns. Let's go ahead and try and eliminate n from both of these equations. Okay, so from this equation, from equation 1, how can we simplify it so that we only have one unknown? Let's see. Let's factor out n from the first two terms in the equation. We end up with n factored out times sine 30 plus 0.8 times cosine 30 equal to m times AC. We want to eliminate n, so we divide both sides by this whole thing. So on the left hand side we are left with just n equals, and on the right hand side we have MAC divided by this whole thing, sine 30 plus 0.8 cosine 30. Alright, let's call this equation 3. Let's do the same thing with equation 2. Let's factor out n. From the first two terms of equation 2 we can factor n out, and we are left with cosine 30 minus 0.8 sine 30, and on the right hand side we have m times g. Divide both sides by this whole thing, and we are left with, on the left hand side, only m, and on the right hand side we have mg divided by this whole thing, cosine 30 minus 0.8 sine 30. Alright, this, let's call it equation 4. Now it's time to realize that we have separated n out from both of these equations. But remember, n is the same thing. N is, in both of these equations, just denotes the normal force being exerted on the road by the car. So they must be the same. So these are just two different expressions for the same thing, n. So equation 3, one expression for n is equal to equation 4, another expression for n. So we just set them equal to each other, right? So equation 3 is equal to equation 4. What this does is just it takes care of eliminating n. So on one side we have the expression of n from equation 3, which is MAC over sine 30 degrees plus 0.8 cosine 30, right? And on the other side we have the expression of n for from equation 4, which was m times g over cosine 30 degrees minus 0.8 sine 30 degrees. Right? Both terms on both sides of the equation have m in it, and m is the same thing, the mass of the car, on both sides. So we can divide them out. Our goal is to separate out AC. So to separate out AC, what we do is just we multiply sine 30 plus 0.8 times cosine 30 to both sides of the equation. So what we have is we have AC left over on this side, and on the right hand side we have a big factor, g times sine 30 plus 0.8 cosine 30 over cosine 30 minus 0.8 sine 30. Alright, this is this big number or big thing, big expression will give me the centripetal acceleration in this problem. And remember, g is nothing but 9.8. This looks a lot dirty, but it is just tedious algebra. If you sit down and practice the algebra out, if you're rusty on your algebra, then this would all get easier. Alright? So if you calculate this out, we end up with an acceleration of magnitude 25.1 meters per second squared. Alright? Now our goal was to find v, the speed, the safe speed for the car, right? Let's go ahead and do that. How do we do that? We know that AC, the centripetal acceleration, is defined in terms of v squared over r, right? We want to solve for v. So v squared, if you multiply r on both sides of the equation, gives me r times AC. If you square root both sides, it gets rid of the square from the left side and gives me a square root on the right side. And both of these are known. R is 50 and AC is just, we calculated to be 25.1 meters per second squared. If we calculate that and square root it, we find that the speed at which, if this car goes, then it will be very near to tipping over, is 35.4 meters per second. As we can see that our chosen direction of friction is actually correct, that it was indeed acting, so this was the car, it was indeed acting down along the plane, because we get a speed which was greater, which is greater than the speed we calculated when there was no friction. Okay? Since the car was traveling faster than the case where there was no friction, this meant the friction would be acting down along the plane. If this speed were smaller than what we calculated before, 16.9 in the case of no friction, then the friction would be acting in the opposite direction, up along the plane. Okay? Because the natural inclination of things on a banked surface is due to its weight to tip over down along the plane. So if there is no friction, the natural tendency of things would be to slide down, alright? But if it's going too fast, that tendency changes to trying to tip over on the left side or the other side, up along the plane. That is how you determine the direction of friction, alright?